Nestled in the picturesque city of Geneva, Switzerland, the European Organization for Nuclear Research, commonly known as CERN, stands as a beacon of scientific exploration and discovery. At the heart of CERN's mission lies the quest to understand the fundamental constituents of matter, from the tiniest particles to the vast cosmic expanse. One of the most extraordinary scientific projects here is centered on the captivating tale of the antimatter factory, where visionary thinkers are stretching the boundaries of human understanding and technological prowess. Antimatter, as we know, is at the heart of a mystery about why the universe exists at all. So, studying antimatter is also key to understanding our very existence. But in a quest to unravel one of the biggest cosmic mysteries, CERN has found something weird happening with antimatter that no one can explain. This finding then leaves a hanging puzzle that scratches scientists' heads. So what exactly did they find alarming? Join us as we dig deeper into CERN's new discovery that has the scientific community baffled. Antimatter sounds like science fiction, a material that looks like ordinary matter but would unleash as much energy as an atomic bomb if even a speck of it came into contact with anything around us. Small wonder that the scientist who first predicted the existence of antimatter felt uneasy about what he had found. Nowadays, physicists are using gigantic particle detectors to probe subtle effects that they hope will explain the central mystery of antimatter. Where has it all gone? It is a question whose solution lies in the very first moments of the Big Bang almost 14 billion years ago. Something happened back then to turn a universe born with as much antimatter as ordinary matter into one strangely devoid of the stuff. Did the antimatter vanish as the result of some strange quirk in the laws of nature, or is it still out there somewhere, making up anti-stars and orbiting around anti-galaxies? One thing is certain. Despite its weirdness and rarity, antimatter is for real. The first hints of antimatter's existence emerged in 1928 when 26-year-old British physicist Paul Dirac announced his discovery of a single equation unifying no fewer than three of the key theories of physics: quantum theory, electromagnetism, and Einstein's special theory of relativity. In 1932, physicist Carl Anderson at the California Institute of Technology had developed a new type of particle detector to study cosmic rays, revealing the trace of a particle behaving as if it were the exact mirror image of an electron, the first sighting of the positron predicted by Dirac's equation. While electrons are ubiquitous, it took a state-of-the-art particle detector to find even a single positron. There was nothing in Dirac's equation or in the known laws of physics to explain why the universe should prefer matter to antimatter. So where was it all? One suggestion was that the Earth just happened to lie in a relatively antimatter-free region of the universe. Perhaps there were whole stars made out of the stuff lurking out there. If so, it would be easy enough to tell. As soon as antimatter comes into contact with ordinary matter, it is totally destroyed in a huge burst of radiation. Matter-antimatter annihilation is the most potent source of energy in the universe, and its effects are hard to miss. So if there really are anti-stars or even whole anti-galaxies beyond our own, the Earth should be bathed in a constant glow of gamma radiation, the telltale sign of matter-antimatter annihilation. The reality could hardly be more different. Since the early 1960s, astrophysicists have sent ever more sophisticated gamma-ray detectors above the protective blanket of the atmosphere to see what is out there. The lack of gamma rays from our own galaxy suggests that the nearest anti-star must be at least 10 light-years away, with no more than one star in 10,000 being made from antimatter. On a larger scale, the absence of antimatter is even more striking. The level of gamma rays coming from distant galaxies suggests that no more than 1 part in 100,000 of extragalactic matter can be in the form of antimatter. But why is there more matter than antimatter? Did something happen during the Big Bang to get rid of antimatter while leaving enough ordinary matter behind to create the galaxies, stars, and us? The first hints of what that something might be emerged in 1964 when American physicists studying so-called kaon particles discovered a bizarre effect called charge parity, CP violation. This meant that antimatter does not always perfectly mirror the properties of ordinary matter. The level of CP violation detected was very small, but in 1967, the brilliant Soviet physicist and dissident Andrei Sakharov showed that it might just explain why matter created in the Big Bang did not pair off exactly with all the antimatter. Physicists are now probing both these questions in gigantic machines that attempt to recreate conditions in the early universe. At Stanford University, California, The 1,200-ton Bobber particle detector is being used to study the effects of smashing together electrons and positrons with violence not seen since moments after the Big Bang. The collisions produce unstable particles called mesons and their antimatter counterparts, whose decay can be studied for signs of CP violation. In 2001, scientists working at Bobber and also at Bell, a similar experiment based in Japan, announced that they had succeeded in detecting CP violation among mesons and their antiparticles, thus showing that the effect is not confined to one type of particle. Better still, the level of CP violation was right in line with theoretical calculations based on the so-called Standard Model, the best theory currently available for understanding subatomic particles. The bad news was that the measured level was far below that needed to explain the observed preponderance of matter over antimatter in our universe. Physicists are taking this as a sign that the Standard Model is lacking something crucial. Precisely what it might be remains unclear, but experiments are already being planned to find out. Astrophysics and particle physics are often dismissed as being utterly irrelevant to everyday life. But by attempting to explain how antimatter lost out to ordinary matter in the birth of the cosmos, they hold the key to understanding our very existence. That's also why physicists at CERN are searching for subtle ways that antimatter differs from matter. Indirect measurements of the effect of gravity on antimatter suggest that matter and antimatter both respond in the same way to gravity. However, the difficulties of working with antimatter meant that a direct observation of antimatter falling freely under Earth's gravity had not been made. For the last 20 years, scientists from the Alpha Group have been collecting antimatter at CERN, siphoning high-energy antiprotons from collisions in the CERN proton synchrotron and slowing them from the speed of light to speeds of a few hundred feet per second and a temperature of about 15 degrees above absolute zero. The antiprotons are then mixed with a cloud of anti-electrons or positrons produced by the decay of radioactive sodium in a so-called mixing trap. Normal hydrogen, the simplest and most abundant element in the universe, consists of a positively charged proton attended by a negatively charged electron. The alpha experiment results in a few atoms of antihydrogen, the nucleus is an antiproton, and a positron circles it. In 22, Dr. H reported that these antihydrogen atoms emitted and absorbed light at the same frequencies and wavelengths as regular hydrogen, just as Einstein would have predicted. Since then, many experiments, all indirect, have strongly suggested that antimatter also gravitates normally. But those experiments have not been conclusive because gravity is less than 1/trillionth as strong as the electromagnetic fields used to manipulate the antiatoms. In the latest experiment, the antihydrogen atoms were confined by a magnetic field inside a 10-inch long metal container. Since, like hydrogen, antihydrogen atoms carry a slight magnetic field of their own, they can be held in place and prevented from touching the walls of the container and annihilating. The alpha team cooled the container and its antiatoms to within half a degree of absolute zero, sapping them of energy and slowing them down. Then the scientists turned off the magnetic field, and the antiatoms, freed from confinement, dropped out of the container. A cloud of regular hydrogen atoms was dropped from the same height. If gravity affects matter and antimatter the same way, the two types of atoms should fall the same distance. This was the result they found. "We were all surprised," said Dr. Fager, the experiment leader and a physicist at Simon Fraser University in Canada. "None of us expected to see no difference between matter and antimatter. This was a clean experiment," he added. "If there was an anomaly, we would have seen it, and there were none. But as Albert Einstein said, no amount of experimentation can ever prove that you are right." The result, of course, does not prove that Einstein is right, nor does it explain the asymmetry between matter and antimatter. However, the scientists' brains were fried because just last year Fermilab physicists reported possible evidence that muons, a heavier and unstable cousin of the electron, are more sensitive to gravity than muons, which may or may not be related to this result. Even if the result was a straightforward confirmation of Einstein's theory, the work would have been worth it, said Dr. Schaefer, who has spent his life studying antimatter. "What makes antimatter so interesting and frustrating is that it behaves exactly like matter," he said. "Nobody can tell us why we live in a universe made of matter. We don't know," he added, "that the universe chose this path rather than some other path. One of the great mysteries. Let's break this down into a more digestible explanation about CERN's work with antimatter, the mysteries surrounding it, and recent discoveries. Antimatter and its mysteries. What is antimatter? Every particle of matter has an antiparticle with the same mass but opposite charge. For example, the electron's antiparticle is the positron. Dirac's theory asterisk. In 1928, physicist Paul Dirac predicted antimatter. He found that his equations describing electrons also had solutions that implied the existence of particles identical to electrons but with positive charge. These were positrons. The asymmetry problem asterisk. According to the Big Bang theory, the universe should have produced equal amounts of matter and antimatter. However, we observe a universe filled with matter with very little antimatter, puzzling scientists about why there's more matter than antimatter. CERN's antimatter factory asterisk. How does CERN produce antimatter? Particle colliders at CERN produce antimatter using high-energy collisions in particle accelerators like the Large Hadron Collider, LHC. These collisions produce various particles, including antiprotons. Slowing down antiprotons asterisk. After production, antiprotons are extremely energetic and need to be slowed down. This is done using a series of decelerators to reduce their speed to manageable levels. Creating antihydrogen asterisk. The slowed antiprotons are combined with positrons, anti-electrons, to form antihydrogen atoms, trapping antihydrogen asterisk. Antihydrogen atoms are trapped using magnetic fields in a device called a penning trap, preventing them from coming into contact with matter, which would cause annihilation. Key discoveries and experiments. Studying antimatter properties asterisk. 1. Gravity effect asterisk. Scientists are trying to determine how gravity affects antimatter. Do antimatter and matter fall at the same rate? This is being tested at CERN. 2. CP violation asterisk. Charge parity. CP violation is a phenomenon where the laws of physics apply differently to particles and antiparticles. This might explain the matter-antimatter asymmetry, but so far, the observed effects are too small to account for the imbalance. Recent experiments asterisk. 1. Alpha experiment asterisk. Scientists have been able to measure the effect of gravity on antihydrogen atoms. They use magnetic fields to suspend the antiatoms and observe how they behave when these fields are turned off. Findings asterisk. Preliminary results suggest that antimatter responds to gravity similarly to matter, but these experiments are ongoing to confirm these observations. Implications asterisk. Understanding the universe's fundamental questions, discovering why there is more matter than antimatter, helps us understand fundamental aspects of the universe's creation and evolution. Technological advancements asterisk. Understanding antimatter could lead to advancements in energy production and possibly new technologies, like those hypothesized for space travel. In essence, CERN's work with antimatter aims to solve some of the most profound mysteries about the universe's composition and the fundamental laws of physics. While they have made significant strides, many questions remain, driving further research and discovery.